Okay, so here we have a problem where it's asking for the shear force and bending moment at C. So if I cut this at C, which side do we want to work? We have two free bodies, a left one to the left and one to the right. Yeah, I think you can see the one to the right is going to afford us some opportunities because I don't have to find the reactions at A. Now, one thing we do have to be concerned about is when I try to cut the structure at C, can I cut it at C if there's a load exactly applied there? It's going to be kind of hard. So this won't look well, but let's see if I can figure it out. So let's say we have one just to the left and just to the right. And I'll let those cuts get as close to C as I can, but not quite at the load. So this will be just to the left of C and just to the right of C. Okay? Everybody see that? So let's start with that one first. So if I look at just to the left, okay, and I'm going to draw the free body diagram of the right-hand side. So the first thing I'm going to do is put my positive sign convention. So I'll have positive axial force, positive shear force, and I'll say this is the shear at C, and then I'll have positive bending moment. And I'll put a little plus sign up there to indicate that those are all positive, just so you remember. See, we're on the left side now.
So is it from C to E?
Correct. So then I have, and since I'm cutting it just to the left, I actually get the force 500 pounds right at C.
Can you explain that?
Yeah, I'm trying to see where you're
Which part?
The positive things.
Well, that just matches our sign convention, right?
But why is the positive going up?
Which remember for shear force, if you look at a block, right? We said positive shear force was what? Down on the left, up on the right.
Okay, gotcha.
I said it backwards. Down on the right, up on the left.
Okay, sure.
So that's how this one matches. So I don't know what the shear and the moment and the axial force are going to be, but I'm going to assume that they're positive there. Oh, and also out here on the end I have this applied moment of 2 kip feet. And these dimensions are 10 feet and 10 feet. So there's my free body diagram. I have 3 equations for that and 3 unknowns. So let's start first now, is I'm going to sum moments at the cut and make sure it's in equilibrium. So now I'm doing statics, and I'm using right-hand rule for positive moment. So what kind of moment is this in that sense? It's negative. So I'd have minus the moment at C. This first 500-pound force, what's the moment arm to the cut? It's 0. It's as close as you can get to it. So basically the moment arm is insignificant. So I don't have to worry about this creating moment, but I do have to consider these 2 forces. And they're creating positive or negative moment? Negative moment. Right-hand rule about the cut. Right-hand rule about the cut. Which way are they rotating? Clockwise. That's negative with right-hand rule. Remember, right-hand rule.
So
right-hand rule.
You're drawing the free body diagram, your movement is going to be positive this way.
Say that again.
You said it. He uses right-hand rules. So every time.
Right-hand rule is right-hand rule.
I understand whenever you're trying to calculate it, but
I set these to be positive bending moment, positive shear force, positive axial force, right? Now I'm doing statics. Different sign convention. For statics, I'm using right-hand rule for moments, not bending moments, for moments. And what's the moment about the cut? This is negative. Each of these are negative, and that is everything is negative. Moment about the cut. Let that steep for a second. This is very common. So again, when I assume directions, just like we've done in trusses and other work, I'm going to assume the positive sign convention for the quantity I'm interested in. So then again, this is positive shear force, not a force, a general force. This is a special force, shear force. And shear force on this side is up, positive. This is a moment, but I'm using it as a special moment, a bending moment. And that is positive bending moment on the left side. Same thing here with shear force. Axial force. Now I'm done. I switch gears to equilibrium of the body. You can use whatever sign convention you want, but I always use right-hand rule. And in right-hand rule, that's a negative moment. This creates negative moment about the cut. This creates negative moment about the cut. And this creates negative moment about the cut. It got very quiet now.
What about that first 500?
It has no moment on it, right? I'm so close to it that it'd be 500 times nothing.
Okay.
It creates no moment. Now, when I sum forces, it will count, but not when I sum moments. So I'm going to have minus 500 pounds, and I'll have the first one will have a moment arm of 10, the second one would have a moment arm of 20, and then way out here on the end is negative 2,000 pound-feet. So solve for the moment, what do you get? It says the moment at C is equal to negative 17,000 pound-feet. Which is 17 kip-feet. So negative 17 kip-feet. And what does that mean? What do we assume the moment at C to be? A positive bending moment. And what is the moment actually? Negative. Does that make sense? Well, let's go back and look at the original beam. How do you think that beam is going to generally displace? Is this free end going to go up or down?
Down.
Down. Probably down, so I'm guessing it would look something like that. What does that look like to you? A smile or a frown? It's half a frown, so it's negative. It's negative moment. And what do we get? Negative moment. So hopefully you'll start getting that intuition, developing that, and help you decide whether this is a correct result or not. So now we can finish this object by summing the forces in the y direction. Now I'm summing forces. So I'm going to assume all forces acting up are positive.
Okay.
So I come over here and look at this force here. I called it VC. Hey, that's up, so positive. 1, 2, 3 forces acting down. 500 pounds. 500 pounds. 500 pounds. Any other forces on the structure vertically? No. So it says the shear at C should be equal to 1.5 kips. And it's positive. That means I have positive shear at C. And last but not least, I'll assume to the right is positive for my forces in the x direction. And in this case, all I have is minus AC. So the axial force is 0. Now if you remember way back at the beginning, I said I can't really get under C, but I can get just to the left or just to the right. So I went just to the left. So now we need to go just to the right and see what changes. So let me write that down. Now that amount that we move is so small that you probably won't even see it in the free body diagram. Now, I still have my positive axial force, my positive shear force, and my positive bending moment. That's my sign conventions.
You're still taking it from E.
C. This is the C side of the beam, right?
To the E side.
But I'm just to the right of C. Just barely to the right. So 10 feet away, I still have my 500-pound force. 10 more feet away, I still have my 500-pound force. And I still have this 2 kip per foot moment. What I don't have is the 500-pound force at C, because now it's on the other body. Because I've cut it just to the right, so now it's on this side. So if I cut it just to the right, you can see I don't include the 500. If I cut it just to the left, I do. So just to the left it's on, just to the right it's off.
Could you do it from A too?
From A.
So from A to the little bit of right of C?
Yeah, you mean could I cut it like this?
Yes.
Sure, but now I got to find all these reactions.
I was just
I thought you were doing when you said left to right.
I'm cutting the beam. We're finding internal forces, right?
Right.
So this is where I'm making a cut.
I know I did that.
And I decided, because it was a cantilever, that we're always going to look at the right-hand side of the structure. Now, obviously, there's a piece equal and opposite. That's the left-hand side. So what changes? Well, let's go ahead and sum our moments like we did before. So I'm going to use right-hand rule. So when I start off, the moment at the cut is still a negative moment. These two forces still create negative moment. 500 pounds is the magnitude, and the moment arms, I left off the distances, sorry, are 10 feet and 20 feet. And then I have the applied couple at the end, which is also negative, 2,000 pound-feet. So when I solve for the moment at C, what do I get? Negative 17 kip-feet. So it seems like the moment didn't really change significantly as I went from just on the left-hand side under a load to just on the right-hand side. The value of the moment didn't change. Let's see how the shear changes. So summing the forces in the y direction, setting those equal to 0. And I'm assuming up is positive. So looking at my free body diagram, I have the shear force acting up, minus 500 pounds, minus 500 pounds. So it looks like my shear at C is equal to 1 kip. So if you compare these two, so the shear just to the left is 1.5, and just to the right is 1. What happened?
We lost 500 pounds.
We lost 500 pounds. Did we lose 500 pounds? No. We passed under a 500-pound force. So it looks like I might be able to kind of say now that it looks like the change in shear is kind of equal to the force. As I move from the left side to the right side, shear changes equal to the amount of force applied. But that's just kind of an anecdotal thing now. Later we'll make that more formal in our definition. But that's just something to kind of keep track of.
So you take either of the answers on the test?
Say that again?
You will take either answer on the test?
There is no either answer. One is right. They're both right.
Oh. Okay.
Because one is just to the left and one is just to the right. So the one on the right is including the effect of this force. So I'm going to add this to here, but so let's look something like this. If I were to make a plot...
So which one did you say was including the force? Would be the one on the left?
Well, all it is it just says that the change in shear from left and right seems to be equal to the amount of the force applied. Mm-hmm. And this force is what? Positive or negative?
Negative.
Negative. So you can see the change in shear is it dropped down, so it's negative. So this seems to be okay, but like I said, it's just anecdotal now. I just kind of noticed it. We can actually find out later that it's true. So if I were to then come to point C and look at a plot for shear, I'm not so concerned about what it's doing on either side, but there is a change, right? It's 1.5 kips on one side, and it drops almost instantaneously to 1 kip on the left, with almost very little difference between them. So you will find that if you were to make a diagram or you were to write an equation for shear, you can have instantaneous drops at forces. So you can imagine what the function of shear would look like across this beam is every time you hit one of these 500-pound forces, what is it doing? It's dropping. So it's going to look like a set of stairs. Yes, Mr. Isbell.
So you said both shears are correct, right?
Well, one is to the left and one is to the right.
Why can't you take the average of
There
the
is no such thing.
I know that. How do you have two shear forces at one point?
That's because it's a point. It's an odd thing to think about a point. What's a point? What's the area under a point?
There is none.
Well, it's infinitely small.
Right.
So all it's saying is that as you approach the force from the left-hand side, you have this shear. Then you hit the force, this weird thing that is acting at a point. Just when you pass it, the shear changes that amount. Now, if I did the same thing for moment, I'll get a kind of a different kind of response. So again, if we're looking at that point C only, I'm not really sure what's happening everywhere else. So don't hold me to the shape of these things. But more than likely, you're going to see at C, what's the moment? Actually, I've got it upside down. It should be negative 17, right? We solved for it. That just means that the moment's coming in at some value and probably leaving at a different value. So the moment is continuous. It doesn't have this discontinuous jump. The only time you'll see the moment jump is at a applied moment.
In this case, then the moment would be a flat line, right? Because we have the same moment at both points.
All I'm saying is that the moment doesn't change at the point as you go from left to right. It's the same value. Other characteristics of the moment will change, and we'll talk about that later. So I just want you to recognize now today that change in shear seems to be related to the load. We haven't talked about change in moment yet, but we'll talk about it as we move forward. So any other questions about that? Okay.